In this lecture, we talk about resistance and temperature. So we link resistance and temperature. So first we denote reference temperature as T0. At T0, you have some resistance R0. So R0 is resistance at T0. So resistance R at some temperature T is given as R0 times 1 plus alpha T minus T0. So T is the present temperature and R is the present resistance of the conductor. So you rearrange this, you get alpha T minus T0 is equal to R minus R0 divided by R0. So you can rewrite this as delta R over R0. So this delta R is nothing but R minus R0. This is equal to alpha times delta T. So we have two cases to consider. Case 1 is when alpha is greater than 0. So this is true for metals such as copper. When alpha is greater than 0, now as the temperature increases, then delta R will also has to increase. Yeah, you're increasing the right hand side, so left hand side also has to increase since R0 is a constant and alpha is a constant. So example of this is say copper. So copper has alpha equal to 3.9 times 10 to the power of minus 3, and the units of alpha are degree centigrade minus 1. So for copper, as you raise the temperature, the resistance will increase. Case 2 is when alpha is less than 0. So this is true for semiconductors. So if alpha is less than 0, that is alpha is negative, then as delta T increases, so delta T is positive, then delta R has to be negative because right hand side is negative, so left hand side also has to be negative. So as temperature increases, the resistance actually decreases. So example of this is semiconductors such as silicon. Here alpha is minus 75 times 10 to the power of minus 3 degree centigrade to the power of minus 1. So for silicon, if you increase the temperature, the resistance will decrease. Now we come to superconductors. Now for some metals or compounds such as some particular kind of ceramic, the resistance becomes 0 below certain critical temperature. Such metals are called superconductors. Now, interesting fact about this is that if you set up a current in a loop of wire which does not have any resistance, then the current will remain in the wire without any potential difference. And will remain there forever. Now we talk about power. First we recall potential energy of a system. So potential energy of a system is given as charge times the potential difference. So Q is the charge and delta V is the potential difference. Now this charge Q has to pass through some conductor. Now when it passes through the conductor which has resistance R, then its potential energy will change. So the potential will decrease when you pass through the conductor. You're going from higher potential to lower potential, but because of resistance also there will be some decrease in potential. Now in small time dt, there is a small change in potential du, and this comes from transfer of small charge dq through the conductor. So you rewrite the equation as du by dt equals to dq by dt times delta V. Du by dt you call as power and dq by dt is the current. So power becomes I times delta V. So this is an important result. So delta V is equal to IR. This you have seen before. So you can plug this in. So you get power is also equal to I square by R. And now instead of I you plug in delta V by R. So you get power as delta V square by R. So this is the formula for the power and it is measured in watts. So now we want to talk about power transmitted through the electric lines. So say this is the power which passes through the conducting wires. So this is the energy delivered to some system, so say to house or office or a factory. Now if large amount of power is required to be delivered and the resistance is high, so if the resistance is high, then we need to keep delta V high. So only in that case we can deliver high amount of power. In fact, this is precisely what is done by power companies. They generally use cheap quality cables, often made up of aluminum, which have high resistance. So in order to deliver high amount of power, they deliver it at extremely high voltages or extremely high potential difference. So to deliver high power, they keep delta V very high. Now in order to use this power, we have to use a transformer so that you can convert this extremely high delta V to a usable voltage like 220 volts. Because delta V in the power wire could be kilovolts and we need only 220 volts. So we use transformers to convert it to 220 volts, which can then be used at our homes.